Hi, welcome to my channel, JaberTime. We're going to go over complex numbers with enough examples. This is about, I would expect about 20 minutes, but with clear notes and clear examples. You will see by the end, if I write this on the whiteboard and cover the same material, it's going to be way more than 20 minutes. So hopefully you like it, and let's get started. When we talk about complex numbers, we have a plus bi. That's the complex numbers. We're going to be using the imaginary unit, I equals square root of -1, because that's not real. There is no such thing as a number multiplied by itself will give you -1. And we're going to use also the concept of the conjugate of a complex number, which is a minus bi. The reason why we have imaginary units and complex numbers is the following. This graph here is x to the second plus x plus 1. As you could see, it doesn't cross the x-axis. So parabolas could cross the x-axis twice. That's two real numbers. Or the vertex will be sitting on the x-axis. That's one real number repeated. Or like this one, we say no real solutions. And if we need the solutions, we're going to use the square root of -1 as an imaginary number I and move on and use complex numbers. That's the reason we use complex numbers and the benefit of solving advanced math problems. So let's move on. What's complex numbers? We have complex numbers and imaginary units to focus on. That's a complex number, and the imaginary unit will be square root of -1. To start with, instead of starting with I and writing a column for I, so it's going to go I square, I to the third, I to the fourth, and I'll show you why I stopped right here and I moved to I to the fifth after in a different color. Let me show you. So I is I. We're not going to write negative or square root of -1. What's I square? It's an I times I, which is square root of -1 times square root of -1, meaning I'm squaring the square root of -1, which is going to cancel the square root and give me -1. So from now on, keep in mind that I square is -1. What's I to the third? I to the third will be I to the second multiplied by one more I, meaning that's a -1. We're going to multiply -1 times I, which is -I. What's I to the 4? Well, I to the 4 is I to the second times I to the second, which means -1 times -1, and that's a +1. So we have I to the second, I to the third, I to the 4, but if you go to I to the fifth, you're going to start all over, meaning it's I to the 4 times I, and I to the 4 is 1. So it's going to be 1 times I, which is I. So it goes back to the start. In short, I have the following. So we have I to the second, I to the third, I to the 4, I, -1, -I1, as you could see. When you go to I to the fifth, you're going to repeat yourself. I to the fifth, 6, 7, 8, it's the same answers. We go I, -1, -I1. If you go beyond I to the 8, to I to the 9 and on, it's the same pattern. So what does that mean, and how could we take advantage of that? Here's an example. Keeping those handy, I to the 4 is 1. I to the 8 is 1. I to the 12 is 1, as you could see. So what's next? I to the 16 is 1. I to the 20 is 1. I to the 24 is 1. How about if we go all the way to 100? I to the 100 is a multiple of 4, the 100. That means it's I to the 4 to the power 25. So it's 1 to the power 25, which is 1. So if you go after I to the 100 one more step, it's like you are standing here and you move one more step, you're going to go back and repeat yourself, so it's going to be I. This is what I mean. So 101 is one more than 100. And that's a 1 times one more step, which is an I to start with, and that's going to give me 1 times I, which is I. What's I to the 99? Stepping back. So if you are here, that's like I to the 100. Stepping back, you're going to be at negative I. Hopefully, you get the idea. It's a pattern of multiples of 4. If you are a multiple of 4, you're here. If you are 1 less, you're going to be here. If you are 1 more, you're going to be on I. Different examples. Simplify square root of negative 100. We're going to split them and take the square root of negative 1 and square root of 100 to start. That's a simple example, and it's an important example for more complicated numbers. The first part is I. The second part is square root of 100, which is a perfect square. That's going to give me a 10. Rearrange. That's 10i. How about if it's not a perfect square? Well, most of the time you have part of it as a factor, perfect square. 200 comes from 100 times 2. So we could take advantage of the previous example and do it this way. So we have the 2 times 100 times negative 1. That's an I. That stays because that's irrational. We're doing a right non-repeating, non-terminating decimal instead of square root of 2. Keep it. Square root of 100 is 2. 10, I mean. Rearrange. And that's the answer. 10 square root of 2, I. How about if they're not that clear, like 100 and 200? Let's say 150. The negative is an I. It's going to give me an I. To see 150 and save you some time, that's why I have the notes written ahead of time. It's 2 times 75, and 75 is 3 times 25. I could stop right there. I just want to show you that tree diagram in detail. So it's 5 times 5. That's a good number to handle or deal with when you have square roots. So if you take your time and display everything in factors, prime factors, we have the following. And we could rearrange square root of 2, square root of 3. Nothing I could do about them. Square root of 25 instead of square root of 5 times square root of 5. That's going to give me a 5. That's a perfect square. The 25. That's an I. We'll put this together. And instead of saying square root of 2 times square root of 3, we say square root of 6. That should do it for this problem. How about square root of negative 98? The negative is going to give me an I. 98, let's break it down here. And see, it's 2 times 49. I could stop right there and say like 49 is perfect square. I don't have to write 7 times 7. But just because it's my notes or my videos are lectures with notes or examples, I'm showing everything. So here we go. So we have square root of 49 instead of saying 7 times 7 like this one right here, 5 times 5. That's going to give me a 7. That stays, and that's an I. Cleaning the answer and rewriting it in one step. That is 7, square root of 2, and I. When you multiply, we need to handle this by itself, and we don't want to combine them first, because if you combine them, you're going to cancel the negatives and you're going to avoid speaking I's. So let's keep them separate for now. This is what I mean. That's square root of negative 1 times square root of 6 times square root of negative 1 times square root of 15. But 15 and 6 so far are not good numbers to handle with square roots, but it's going to happen. I'll show you. That's an I, that's an I. So we have I square. Let's put the 6 and 15 together in one square root. Let's break this down to 2 times 3, and this one 3 times 5. And now you notice that we have 2 3's. That's a 9. That's a perfect square. And that's why I say, like, early you don't see it, but usually it happens. Square root of 9 is 3. Square root of 2 times square root of 5 will make it one piece. We call it square root of 10. And that's what we have. Final step. Square root of 9 is 3. Rearrange and write it -3 square root of 10. Okay, here's another example. That if I want to solve, I need to move on and use complex numbers and imaginary units. In lower math, when we graph this, that's an x to the second, which is a parabola, plus 81, that's shifted up 81 units. And you want to see like if it equals to 0. No, it's not going to equal to 0 because you're not crossing the x-axis or touching the x-axis. But here we're going to move forward and use the following concept. Let me show you. So when you move the 81 to the other side, that's a negative 81. In lower math, we say no solution. And it's supposed to say no real solutions. But how do you handle this? Well, we know that if x to the second equals k, x by itself will give you plus minus k, the square root of k. Why is that plus minus? Because if you have x to the second equals some certain number 9, like k for example, that's 9. If you need the y's or the values to be at 9, you're going to be up here. Applying this method, you have x equals plus minus square root of 9, which is plus minus 3. The graph will show you. So when you are equal to 9, you have two answers at 3 and -3. Going back to the problem. That's a plus minus square root of -81. And negative will give me an I. 81 is a perfect square. It's going to give me a 9. And rearrange. We have 9i with a plus minus. So two imaginary or complex solutions. Let's take a simple example. That's adding complex numbers. 2 plus 3i plus 5 plus 8i. We add the real part to the real part. That's a simple way. Adding is always easier than subtracting or multiplying. We add the imaginary part to the imaginary part. The reason or the meaning of that is we add 2 and 5. So let's rearrange and show you. That's 2 and 5. The imaginary part with the imaginary part, they go together. That's a 7 and that's 11i. That's a quick example. How about if you subtract? When you subtract, you have to be careful with the minus sign and distribute it to both terms. So here's a minus. Applying it is going to be -4 minus or take away a subtraction of 10i will be plus 10i. Now we go back to the same like last example. We look at the real parts and we combine them, imaginary parts and combine them. So I have 8 minus 4 and we have 3i should be combined to 10i. 8 minus 4 is 4. 3i plus 10i is 13i. Now the following example is division. And for dividing, it's going to take more steps because you're going to be using multiplication. You're going to be using combining real parts, imaginary parts. You're going to be using I squared equals -1. So it has all of it. Let me show you what do I mean. Here's the example. To simplify 5i over 3 plus 2i, we're going to rationalize the denominator. So we multiply the denominator, which is the complex number 3 plus 2i, times its conjugate. To do that accurately, we have to multiply top and bottom side to keep the equal sign. But before I do it, on the side, the concept is coming back from the difference of two squares. A plus b times a minus b simplifies to a squared minus b squared. So what about if you have an I? As you can see, they behave the same way, but this one simplifies to plus. And here's the reason if you need to know why. So if you take your time and multiply using distributive, or using this method, that is my first part, that's my second part, and with the minus in between. Square, 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 square with a minus in between. Applying the square to I and to B, I square is going to give me a minus 1. We know that, and that's going to change this to plus. As an example with numbers, instead of worrying about all the steps here, just apply it this way and you'll be fine. 3 plus 2i. I took this from here to save some time instead of making different numbers. If you notice, it's part of the problem. This way, when you go back here, we'll have less steps to finish the problem. So to do this and apply this rule, we're going to say a squared plus b squared. And that will be 3 squared plus 2 squared, which is 9 plus 4, and that is 13. So the denominator is going to be 13. So I need still to multiply the top and use distributive. 5i times 3 and 5i times 2i. Don't forget the minus or the subtraction. I times I will give you I squared. 2 times 5 will give you 10. 3 times 5 will give you 15. And we have 15i minus 10i squared. Let's use I squared as negative 1. And that's going to change this to a plus 10. Okay. Rearrange. Instead of writing 15i plus 10, I'm going to write 10 plus 15i. Split them into two parts. The real part and the imaginary part, so you could see it as a complex number. And that should do it. So division has a lot of steps, as you could see, but you got to be careful with the minus sign and use of this when you apply the conjugate. Let's take another practice of multiplication with different numbers like this one. So 3 plus 2i times 7 minus 5i, we're gonna multiply them. I'm using different colors to show you what I'm doing. 3 times, then I'll go to 2i times, and 2i times. So 3 times 7, 3 times negative 5i, then we'll move to the 2i times 7, and 2i times negative 5i. The first part is 3 times 7, which is 21. Second part is negative 15i. Next we have 14i. And finally, or the last part, negative times positive is negative. 5 times 2 is 10. And we're going to have I squared. But I squared is negative 1. And negative 1 times negative 10 will make it positive 10. So all these are the same for now. Focusing on this, that's a plus 10. Combine like terms. I have real parts 21 and 10, which is 31. Negative 15i plus 14i is negative 1i. And that should do it for this problem. So division problem is, I showed it to you and it's kind of lengthy. But if it doesn't have both parts in the denominator to see the conjugate, it's a little bit easier. So you don't even to think about the conjugate. Let me show you what I mean. So to simplify this, you could multiply by 2i on top and bottom side, or the conjugate is minus 2i. But why would you multiply by minus or by 2i? You just need to cancel the I from the denominator. And an easier way, just multiply by I. So if you multiply top and bottom side by I, what do I get? Bottom part is 2i times I. That's 2i squared. That's my focus. I squared is going to be negative 1. Top part, you just do distributive. 7 times I. And 13i times I. Don't forget the minus sign. And I squared is negative 1. I squared is negative 1. And that's going to make this positive. And that's going to make this negative. Rearrange. Split them into two parts to see the complex. That's negative 13 over 2 minus 7 over 2i. We're almost done. And here's a different type of example. find the values of x and y. That makes the equation true. Well, to make this equation true, let's make it simple, then we'll come back. I'll show you what do I mean. If you have two complex numbers that they are equal to each other, that says that the real part should equal the real part. And also the imaginary part or unit should equal the imaginary unit. Meaning, excuse me, meaning A should equal to C and B should equal to D. So for a simple example, if you have 5 plus 7i equals to 5 plus di, well, 5 equals 5, so I'm not worried about the real part. But look at the imaginary units, 5 and d. That says 7 and d should be equal, meaning 7 equals d or d equals 7. So it's a simple process. It's not too hard. The only thing is you need to not color things, but just focus with me and see the real part with the real part, the imaginary part with the imaginary part. Here it's not fully clear, so let me clear it for you. My understanding is that x plus 1 don't have i's, so that's the real part. That's the imaginary part. 2 lines, as you can see, underlined. And this right here, the real part is 3. The minus 6i is what I'm looking at, the imaginary part. So with that in mind, we could say that the real part should equal the real part. That's x plus 1 equals 3. And the imaginary part should equal the imaginary part. 2y equals negative 6. That's going to give you subtract 1, subtract 9 equals 2. And on the second part, 2y equals negative 6. Divide by 2, divide by 2. Y equals negative 3. If you notice right here, my notes are clear with colors. I try my best to make it in less time. That's why I write my notes before I start recording. Because if I go over all these examples on the whiteboard in one video, that's going to be a way more than 23 minutes. This video is about 23 minutes, I would expect. But I'll break it down into time stamps in the description below. So if in case you need the multiplication, you jump to the multiplication. Addition, you'll jump to the addition, and so on and so on. Hopefully that was helpful, and I'll see you in the next one. Thank you.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.